Okay, so now we're going to study the extreme points of standard form, and we need one basic concept as a foundation. Let's talk about basic solutions. So we have a standard form linear program now. Let's assume we have m constraints and n variables. Okay, so that means if we express our standard form in these matrix notations, then our A matrix has m rows and n columns. Okay, m rows and n columns. And we further assume that the rank of A is m, which means all the rows are linearly independent. Okay, so to assume that, of course, we need to justify that we are not assuming too much. Basically, that's simple. Suppose you have some linearly dependent rows, then you do some row operations to eliminate them. Okay, we need some careful investigation about that, but that's the basic idea. So, if you are convinced, then let's proceed. Let's say all the rows are independent. Okay, and then that immediately requires you about your m cannot be greater than n. The number of rows must be smaller than the number of columns. Otherwise, your rows cannot be all independent. And then, because the problem with a square matrix is trivial, well, that means we need to have at most one solution. So we're going to assume that m is less than n throughout the following semester. So now for a system Ax equals b, we know this is some basic linear algebra, right? In linear algebra, we spend a lot of time talking about how to solve a linear system. Today we have a system that is special because there are more columns than rows. So roughly speaking, it would have some shape like this. This is your matrix A, which has more columns than rows. Let's select some columns to form a so-called basic solution. So our plan is the following. I'm going to say that if we have a basic solution which follows or satisfies the two conditions here, then we say it's basic. First, it should have n minus m variables being equal to 0. So I first select n minus m variables to be 0. And then suppose the remaining m variables can satisfy Ax equals b, then I'm done. So graphically, we know that just means if I have a linear system like this, then I'm going to split the matrix to two parts. For these n minus m variables, I'm going to set them to 0. For the other m variables or m columns, I'm going to solve an m by m linear system, okay, to get typically a unique solution. So we call those n minus m variables chosen to be 0 as non-basic variables. The others are basic variables, and we say the set of basic variables is called a basis in linear programming. So that m columns would form a non-singular or invertible m by m matrix AB. Here, AB is just a notation to talk about this particular square matrix. But why do we know it is non-singular or invertible? It's because that we know it is satisfying Ax equals b. So if it is not invertible or singular, this is impossible. Okay, and then we're going to do some more notations. Xb is the set of basic variables. Xn is the set of non-basic variables. So X is a combination of Xb and Xn, blah 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 blah. So in general, our Xn would all be chosen to be 0. And Xb, given that AB times Xb equals b, Xb can be easily expressed as AB inverse times b. So let me quickly give you an example. Suppose we have our favorite linear program like this. I want to minimize 6x1 plus x2, 8x2, subject to x1 plus 2x2 less than or equal to 6, and 2x1 plus x2 less than or equal to 6, and all others are non-negative. Then we have this graph, or you can call it figure, that here is our feasible region, and here, because we are talking about solutions, we don't really worry about the objective function. Now, first, we know we are able to translate it into a standard form. Here, basically, we just need to add two slack variables. Okay, so x3 and x4 are slack variables, and we have a standard form. And then, in that particular standard form, we have our A matrix, which has 2 rows and 4 columns. Okay, that means when we want to have a basic solution, there should be n minus m, which is 2 non-basic variables, or 2 basic variables. Okay, so we have 2 rows and 4 columns. We want to select, for example, these 2 to be the basic variables, and these 2 as the non-basic variables, just as an example, so that we have a square matrix here, which is called AB, and then we want to solve ABX equals B, or ABXB equals B. Hopefully that linear system has a solution, or hopefully AB is invertible. Okay, so then for steps of obtaining a basic solution is just to first choose a set of m basic variables to form this basis, and then set the other variables to be 0, so that we may focus on this particular linear system. And we always know how to solve it, right? A n by n linear system can be solved with Gauss-Jordan elimination, and then we know whether it has a solution or no solution. For this particular example, we should solve a 2 by 2 system, just like this. Okay, so we have 2 equalities here. Suppose we choose x1 and x2 as our basic variables. Okay, we choose them as our basic variables. Then we would remove x3 and x4 because we set them to 0. Then we want to solve this particular linear system, or the remaining linear system. Immediately you get a solution to 2. Which means we have a basic solution associated with this basis as 2, 2, 0, 0. Basic variables, non-basic variables. Or we may choose x2 and x3 as our basic columns or basic variables here. Then we remove x1 and x4. We solve the remaining system to get 6 and negative 6. That's going to give us our basic solution where x1 and x4, okay, x1 and x4 non-basic, they are 0. And for basic variables, they are 6 and negative 6. And that's how we get another basic solution. So now you should immediately see that because when we want to get a basic solution, we need to choose m out of n variables to be basic. So we have at most n choose m possible ways to choose different bases, and then we may have at most n choose m basic solutions. In this particular example, we have exactly that many bases, but sometimes we do not, because sometimes some set of basic variables do not give you an invertible B matrix or AB matrix. In that case, it's not a basis. So that's why here we say at most. So if we completely enumerate all those possible basic solutions or basic bases, then when we set a basis, we set other variables to 0, and then we solve a 2 by 2 linear system, put numbers here, and then we get a basic solution. We continue to do that, then we get all the basic solutions. Even if you have 10 variables and 20 constraints, or 10 constraints or 20 variables, you know how to do this. Okay? If you have a computer which can do loops, then you can do that. So basically, if you have enough time, enumerating all the basic solutions can be done.